Hello, everybody. This is Steve with YouTube's C64 Brain channel. I want to thank you for being here today as we go through this Commodore 64 game project video 3. And we are finally getting the sprites up on the screen. And we're going to be learning about the deltas and also covering the CBM PRG Studio sprite editor. So let's get this started. In this series, we're going to introduce the next video in the series, Commodore 64 Game Project Video 3. And one of the goals of all my videos is obviously you're learning about a semi-language game engine, but in no way am I going to be trying to teach you all the fundamentals of a semi-language. That would take a lot of time. So the best way to do that, as I mentioned from video 1 and maybe in other videos, is to find a good book and just start kind of looking it over and learning about simple things, putting together small little projects and stuff like that. But you'll learn about assimilating language concepts in these videos. Okay, as always, you can subscribe to my channel, and the Facebook is available here too if you have questions, and I appreciate your subscriptions. And here's my GitHub, as always, where you can go ahead and you'll have access to all the files that I have for the actual projects that get released out here. All right, so what will be learned in video 3? The goal of these videos is to empower you to create your own games and projects. In this lesson, you will gain the following skills. An introduction of sprites, which includes using the sprite editor to read in sprite data. Then much later, we will learn how to place them on the screen with the subroutine init sprite anim. An enhanced knowledge of map deltas will be explained in player.asm to show why it's important to track these values as the map scrolls. The sprite will also move in harmony with the scrolling screen. Finally, the subroutine sprite to char POS will be used to position the sprite to match the position of a tile placed in the map area. This will be useful later when we need to detect sprite collisions against screen objects, which will be in a later video. And here's the Project 3 flowchart. You can see in this series we've actually added the player init, and this player init includes the sprite to char POS, and we've added update player, which actually springs off to another subroutine player state idle, which you saw in the last video, but we're adding more stuff to that file now. And then inside of there, we're calling init sprite anim. Like I said, we're not going to do any animation in this, but this is needed to get the sprite placed on the screen for now, which is what the set sprite image does. And here's the VIC registers, of course. And here's the changes made to main.asm. The project variables, you can see I'm now including more sprite variables. This is because we need the sprite located in memory where it exists at. Because remember, we moved the VIC bank and we have those sprites at 5C00. So now we're just calling those. And this is allowing you to access all 7 sprites from 0 to 7. Even though in this example, you're only going to see 2 sprites, 0 and 1. And these are called sprite delta offsets. Essentially, as I mentioned earlier, they kind of determine the position of a sprite against an object in the map. And you can see I wrote here, sprite delta variables are defined here to begin a sprite's character X and Y positioning within the screen area inside the border, since we only care about the sprite that is seen on the map. The subroutine sprite to char POS will be reviewed later, which utilizes these variables to find the offset of the sprite's X and Y coordinates. And here's some variables just to show you the sprite being turned on. That's the first one for VIC sprite enable. The next one is making the sprite wider, where it says extend. And then now we're going to call our first subroutine that we've added to this one, which is player init. And this sets up the sprite colors and position on the screen. And you'll see that covered here very shortly. And for the main loop, we've now included the wait frame. This is going to be used to, actually that one may have been the same, but it's actually being used here now inside of our main loop to keep track of our map as it's scrolling with the sprite. And also we've got the update scroll. This is going to determine which way we're scrolling. And then we've also got the update player, which keeps track of the player animation on the screen. And of course, down below there, you can see the file that we are now including is sprite_routines.asm. And the CBM PRG Studio Sprite Editor is how these sprites are being created. They were extracted from the Indiana Jones of Temple of Doom game, but they're being implemented in here, and I kind of modified the sprite. So here is where we read in each sprite shapes, idle, pull, climb, walking, left, right, and so on from the CBM PRG Studio's built-in sprite editor. And you're going to see that when I actually come up with the code example. I'll try to remember to include it in there. A sprite is an area defined made up of pixels ranging from 0 to 24 going across and 0 to 21 going down. Sprites can roam free over the background without interruption and are independent from the characters you see on the screen. You can place them anywhere. You can place anywhere between 1 to 8 sprites on the screen without using multiplexing advanced techniques. Although sprites do start with 0, but I want you to know that there's actually a total of 8 sprites. To access the sprite editor within CBM PRG Studio, you can double-click in the Project Explorer window on the left, or click in the icon in the upper right-hand corner. It looks like a grid to open a blank canvas. The next screenshot will show you what the sprite editor looks like when it's open. And you can see down below here, I'm reserving the hex area for 5C00 for our CBM PRG Studio sprites. And in this example, there's only going to be 6 sprites here. And really, we don't even need that many. We're just including the idle one. So really, we only need 2 because the sprite has no animation at this point. And here's what it would look like when you open the CBM PRG Studio with the Indiana Jones of Temple sprite data loaded in. And if you look up here, you'll see that there's actually 110 sprites, although we're not going to use them in this project yet. Not in this example, but much later. As we continue, the enemies and all that stuff will exist in here. And I won't go into that example, but I'll probably say that for the code example. Sprites used in the project. In this project, the sprites have been imported from a file created with the Vice Snapshot. This is a feature in the Vice C64 emulator that allows you to extract sprite data from a game and saved as binary data. The sprites have pixels ranging from 0 to 24 across and 0 to 21 pixels down. CBM PRG Studio has a built-in sprite editor which saves you the drudgery of calculating the rows and columns using powers of 2. For basic programmers, though, the next slide will show how this actually works. The sprites to the left were extracted from the game Indiana Jones and the Temple of Doom. And you can see right here, I've got sprite 0, that's the head sprite, and then we got sprite 1, that's the body sprite. So there's 2 stacked on top of each other. Creating a sprite. The graph below shows an empty sprite sheet. To create a sprite, you need to fill in the squares. To calculate the sprite data, find the bit data values and calculate them across in blocks of 7s, 0 to 7. So for example, if you filled in just the first 2 squares on the left, you would have 128 plus 64, which is 192. Continue to add these up in columns from top to bottom until you have a complete sprite. The rows range like this: 128, 64, 32, 16, 8, 4, 2, 1, which are in powers of 2, because 2 times 2 is 1, 2 times 2 is 4, and then so on. Here's an example of a closer-up sprite. A blown-up multicolor sprite will look somewhat like the picture below. This is sprite number 0, the head, which draws the top part of the sprite. The blocks going from left to right do not increase to 8 in each row, since they are multicolor and take 2 bytes each, which are known as bit pairs. So instead, they are laid out in 4s. This could be explored in a multicolor lesson later. And I put a little chart up here to kind of show you, for those who may be like, what is this supposed to mean? So these are the binary values that are being carried out for the multicolors. And you can see what each one does. This handles the background. This handles sprite color 0. And this one handles multicolor 1 for sprite and multicolor 2. And I even put the colors here to show you how they correspond with the CBM PRG Studio. Okay, now we're going to read up the file player_routines.asm. And these are the changes we've made to it. So right here, since we're now including a sprite, we're going to be using the one we saw earlier, player init. And inside of this area, you can see we have some code here that's going to actually take care of the background colors, border, and it's also taking care of down here the multicolors. And further down, you'll see sprite colors and stuff like that. Those are for the, one is for the top sprite, one's for the bottom sprite. And then you can see here, what this is doing is just showing you how to position a sprite using the subroutine we're going to look at later called sprite to char POS. And if you look carefully here, I kind of explained a little bit up here. This is how the calculations are going here on the sprite. But essentially this 19 easily is just the X position of our sprite here and our sprite here so that they both stay stationary with each other. And then down below here, you'll notice that there's a param, so it's saving it in this variable. And then we've got 0 and 9 down here. So this essentially is going to keep track of the vertical position, which is 9. That means it's going to start at 9 because, as you'll learn much later in the coding example, this is taking a sprite and pushing it down to calculate in a row of 8 by 8 so that when the sprite's moving, it can bump into characters. So the 9 represents where the sprite is here. And if you go down a few more here, and this is probably a good example, I got it split there. You can see down here it says 11, and that's the sprite Y position for sprite. Sprite 1. That's why I put Y1 and I put Y0 here, the head and the body. And down here, this is the sprite active states. It lets you know whether the character is alive or not, or someone is killed the player. And then down below here, we have the caps area. This keeps track of the position of the sprite at this point on the screen. So as the sprite's walking around the screen, goes too far right or too far left, the screen will start moving in that opposed direction. And now we're inside of the update player, which is the new one we added. So this is going to keep track of whether we're going to launch from this routine if the sprite is active. If the sprite is still alive, then we're going to execute from here. And you can see if he is alive here, it goes down here to update and it launches our main routine for our sprite, which is player state idle. Now here's another routine that's actually included. This is the move player right routine. And this is going to allow the player to move, to move right here in this case. So I wrote, deltas are introduced here. Deltas are used to track the position of the scrolling screen and are necessary to track the range of the sprite's movement. As I mentioned earlier, as that sprite's moving across the screen to the right, we want to also know its sprite delta because we want to know if it's bumping into another character or not. And if you want to look at video 1 more, you'll see, hopefully learn a little bit more about deltas as you go along, because deltas, depending on where your level of assembly language is, can take a moment to grasp them. And this is basically the delta saying if it's hit 1, it means at this point we don't scroll or move because we basically bumped into the wall at that point, which is why it's saying scroll right here. And this is the left movement. It's the same as the right, except it's going to the left. This is the down movement. And you can see here it's checking for a 2 as it's going down on the delta. And this is the map delta going up, or move player up. And this is what's called the player's substate variables. States are necessary to know to evoke a specific action. In the examples below, the first variable determines that a state has begun. The last state means it is now active mode unless we turn it off by clearing it with a 0. So basically whether it's active or not. And here's the player state idle. These are the updates being made to this subroutine, which again is our main subroutine for our sprites. This is just going to let you know in this substate whether or not the state is active and running, then we continue to the running part. Okay, now down here below, this is something brand new, which I'll probably go into more example in the code example here. But what this is essentially doing is just calling an animation table that's been generated in the code to allow it to check where the animation is in a state. So the animation is going to be changing the sprite as it moves. You'll see it walking and stuff like that, or whatever the state is, whether it's swimming, and that just changes as it cycles through this animation state. And you can see here it's storing, high and low and high bytes there. Okay, so since we are now adding a sprite to our map, we have included an extra move player right subroutine. The first one, LDX number 0, positions sprite number 0 on the top, known as the head. The second one, LDX number 1, positions sprite number 1 below that, known as the foot. As you saw earlier with the sprite split up, this is the same thing. The 0 is sprite 0, and the 1 is sprite 1. And that's just how you get them both positioned on top of each other. So this is a stacking area you're looking at. And here's another example. Quick intermission here. The code earlier, and I just showed you this one, just to show you exactly what's going on here. So here's the first one, and here's the second one. And I kind of broke them up there to show you. Represents the sprite data is seen here, and I put sprite number 0, which is the LDX number 0, is the head, it's the top part, and then you call the JSR move player right, so he can move that part of the sprite right. So this is essentially allowing this top part to move right, and this is calling sprite number 1 to move this one to move right, so they move in sequence with each other. Okay, for now, the player's shape data will be the same idle sprite as the joystick moves the sprite around the map. In the next video, we will introduce animation, and the sprite shape data will change as the direction changes. So this is the left movement routine. The same thing, the head and the body. And here's the up movement. Same thing, except now we're just going up with the two different sprites. And here we're going down with the two different sprites. And of course, now you see the variables for the initialized for our states. Now we're going to look at a more complicated file, which is the sprite_routines.asm. And to try to explain this one would probably take a little bit more time, because you're basically looking at data, or what are called bits, as the sprite is moving across the screen to determine whether or not it's reached what's called the MSB point, which is the most significant bit. So once the sprite passes over the lowest bit, which is 255, it has to pass over to the next highest bit. So the carry flag has to be generated. And this code is allowing all that to take place, essentially. It's just working at a table to track where that sprite is moving, whether or not he can cross that boundary area. And you can see right here, this is where it flips the bits and it stores them. And it shows right here, if it started with 1, it would flip it to this. Otherwise, and it saves it here, of course, and this is the position of the sprite on the screen. Otherwise, if he's at 30, that means he's trying to go backward this way, and now we're just going to reverse it. And down below here, here's some more code to kind of show you. This is more of how the math is being done. So this actually gets really interesting here, because what this is doing, as I mentioned earlier, is taking a sprite, which we know goes from 0 to 24 across and 0 to 21 down, and is compressing that to fit into a smaller area mathematically. Now, it's not changing the bits of the sprite in any way, but it's changing the math behind it so that it lines up to an 8x8. So when the sprite is moving, the values are equal to what is being collisioned into, whether it's colliding into a wall, it's reaching a pole in the game, or whatever. And like I said, this is just the math here. So this is the x variable being calculated. You can see here we're multiplying by 8. We're getting the value of 24 here, which basically is subtracting the edge of the screen. And that includes the border over here, because we only want to see what's on the actual screen. And this down here, param2, is the y position. So we're kind of doing the same thing here again, multiplication by 8. And this time, the top is a little bit bigger, so it goes down to 50 here. So we're just subtracting off the delta offset from that to get that positioned on the screen as well. It's how the math works. Okay, sprite and character alignment. A better explanation of sprite to char POS is that we need to have a way to later detect when our sprite bumps against a wall, pole, and so on, as I mentioned. A sprite's position at X and Y does not align with the tile that occupies the screen area going from 0 to 40 across. So a special type of math is performed, and in Viola, we now have sprite data that is perfectly aligned with character data. And I'm showing you an example here again. This is our 24 by 21 sprite. You can see 24 here, and I just graphed it showing down. and there's our head sprite, right? And this would be like this would, let's say this is a sprite's head and this is a sprite's feet down here. So this is it bumping against a tile here. And of course, these are the deltas 0, 1, 2, and 3. That's how you know where you're at in the deltas. And it's going to determine the alignment here of this. So as the sprite's moving up against here, it's going to have its own different type of data because of that border, because the sprite can go off the screen up to a certain position. By the time it gets on the screen, it may be at like 0 already, because if you're counting, 40 or something, it says it's counting from 0, 1, all the way up to 40. But the character data on the screen here actually starts at 0, so that math is necessary. And I wrote, you may notice that it appears that the tiles are 4 by 8. This is because they are multicolored tiles and 2 single pixels side by side make up a bit pair. And that's just how the calculations work inside of the charpad. Set sprite image. Oh, so this one is actually going to put our sprite on the screen. And like I said, I'll probably go into more example later in the code. But I just wanted to show you this is how we are basically loading in the frame of our sprite. Or it's essentially the image to show where that sprite is located at in memory so we can position it and see it. This one is our knit sprite anim. This one will be taken advantage of more, but for now this is being used since it actually calls the sprite, the one you saw earlier, to the screen. But essentially this routine right now is not really being used or anything. It's not activating any counters or anything yet until we actually get the sprites moving. Like I said, I was taking these videos in sequence so that we can see a simple sprite on the screen and break it down later to show you how animation works. And here we got some more code going on for the animation, not being used, of course, but you see the main one here is our JSR site sprite image, which is essentially sitting inside the animation subroutine. And here's some more code for it. And you see there's actually, if you look at the one here and earlier, you would have saw sprite 0, X, right? And then down here, you'll see add with carrier 1. So this is keeping track of that sprite 0 and sprite 1 as well. Down here, now we just got the sprite tables data. And we have also got all the other sprite animation tables. The active tables are at the top here. And underneath that, we got the sprite position table data. And then we had the position X delta, char POS X deltas, and sprite delta trim X, sprite POS X extend. So these are all just being used to tell what's going on with those bits in the sprite. And here we got the sprite POS Y tables, sprite POS Y delta tables, sprite char POS Y table, sprite anim timer, which is not being used yet. But you can see again, these bits values will be changing and loading in those different images so that we can get that animation going. And these are timing that's actually going on with the sprite. And then we got sprite anim count. And this one, I think, is a pointer to which one is being active. And then, of course, at the bottom here, we have sprite animation. And that's a 16-bit word. Sprite animation tables now. You can see these are the loops that are actually allowing the animation to loop and continue over and over again. Sometimes like a falling animation may have like a loop animation. This one is used type play once. Like, for example, if you throw a punch, you only need to see it once. You don't need to keep doing it in rapid succession unless the player is continually pressing the button. And then we have type ping pong, and this is kind of like a ping pong ball if you think of a ping pong ball going back and forth for the sprite animation. And then we got anim player idle. And you see the data for this. Now, these are going to be really important because anytime you change a sprite's shape data, you're going to create tables like this. This one is just showing as a player is standing still. If you looked at any of my other examples that I have played in the background of the previous video examples, you saw the sprite kind of moving back and forth when he was just not doing any movement. He's not moving left or right. You saw him moving kind of his feet up and down. And that's exactly what this is doing. It's just a post animation position, but we can use this to control the right movement, up, swimming, whatever we put into the game. Okay, summary of topics covered. In this video series, you learned how to read in sprites from the CBM PRG Studio editor and place them on the screen, matched into 4x4 tile alignment known as sprite XY to character XY matching. Then we learned about the proper positioning of map deltas as the screen shifts to track where the area of tiles move into. Thank you for watching. I want to personally thank you for watching this series and subscribing to this channel, subscribing to my Facebook page, and just being here today. It is people like you that help keep the Commodore 64 alive after all these years. Feel free to share this video with your friends, family, or anyone who finds it interesting to create their own game project for the Commodore 64. Hi everybody, in this video series we covered on the Commodore 64 game project video 3, learning how sprites are placed on the screen from its actual position and then to match character data in an 8x8 matrix so that when a sprite's moving on the screen it's going to bump against a wall and so on. And we also learned about the CBM PRG Studio Sprite Editor and saw an introduction to that. And essentially, we got a little bit covered into kind of how to position the sprite on the screen with the set sprite image. And we're going to be covering, of course, animation and stuff like that later. So this is a pretty simple video. So I hope you guys enjoyed this and look forward to the coding example here where we're going to be able to see the actual project in motion. Thanks for watching, guys. I appreciate you so much, all your subscriptions. And I'll see you guys on Facebook. Feel free to leave the comments here as well. Have a good one.